Okay, so we're going to go from Y to a delta, and let's do the center tap orientation to really kind of drive this home. So I'm going to have a neutral that runs to ground. We'll run it to ground in this situation, as well as out to our customer. That's the neutral line. I'll use some different colors to help here. Now remember that these are a transformer. The symbol is like this, right? So it's induction that's happening here, from here to here. So these phases really have no effect on the bottom phases. Well, these phases I'm going to label as a different notation. I'm going to use lowercase letters. They do have an impact on the bottom phases because the currents from the big A will go to the phase of the little a, right? And I'm via the magnetic induction here, I'm going to induce a current in this line. But they're separated by air. So why not use lowercase letters here to distinguish that? So let me first draw up this B connection here. And then I'll go from here to here. And we can see what that allows me to do is I'm going to have half a coil in between the B and C phase. So I can draw B and C. And then these are going to be sent out to the customer. As 120 volts in this application. Now what about our high line, right? Our high leg voltage. Well, that's going to have 1.5 coils in between. So we're going to run from here, skip all these to here. And this is A. And we can see we have 1 full and a half, which is to neutral, which will be our 208 volts, which we can also send to the customer. So this gives you a more practical look at this. And also notice that, remember for our center tap, let me just draw this out really quick. And then I tap this one, so I divide it in two. 240, 240, 120 volts. So if I'm center tapping to neutral, this is 240, but it's divided in two, right? So each of these is 120 to neutral. And I'll see half a coil going from B to neutral. And I see half a coil here going from C to neutral. I also see a full coil in between B and A, which is represented here. And I see a full coil between C and A, which is represented here. And I see 1.5 coils from, here's half, and here's 1 to A, and here's half, and here's 1 to A if I go this way, half, and 1 to A if I go that way. Clean this up just a little bit. So now we can see how this would look on an actual transformer if we're the linemen and we're up there connecting wires. And this sort of understanding is intuitive because you wrap your head around the abstract as well as the practical. So I hope this made sense to you guys, and I hope this was offering some value to you. Now that you know all the differences between this, one more thing that I wanted to mention here too is that you can quickly calculate the turns ratio of a transformer just by looking at these voltages. So if I go 480 volts to 120 volts, what do you think the turns ratio is? Well, a neat trick here is that the turns ratio is exactly proportional to the voltage ratio. So if my voltage goes from 4 to 1, right, 480 to 120, then my turns ratio is going to be 4 to 1. And I'll have more turns on the high side. Right, it's almost like a capacitor. The more space you have in between and the more turns, the higher the voltage. So this is a 4 to 1 turns ratio. Easy calculation for this problem. I hope this made sense.